Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi and today we are going to discuss about the module Diffusion Pumps from the paper Thin Film Science and Technology. After studying this module, you should be able to understand about the diffusion pump. That means we'll have first an introduction and then the principle of operation. Secondly, we'll learn about the working principle of diffusion pump. The next we'll know about the parameters influencing the functioning of diffusion pump. Next we'll study about the advantages and disadvantages of diffusion pump. And in the end we'll see how to start the diffusion pump and what are the steps which are involved while shutting down of diffusion pump. So before going into the detail, let's have a brief introduction. The necessary condition for the scientific research and modern high technology lies in vacuum physics. Vacuum comes from the Latin word vacua, which means nothing or empty. Therefore, there is no ideal vacuum since a totally empty space does not exist in nature. Thus, a partially empty space is considered as vacuum, where some of the air and other gases have been removed from a gas containing volume. Gas comes from the Greek word chaos, that is infinite or empty space. In other words, vacuum means any volume containing less gas particles, atoms and molecules, a lower particle density and gas pressure than there are in the surrounding outside atmosphere. Therefore, gaseous environment below atmospheric pressures is known as vacuum. Existing of high vacuum is the essential need for the thin film deposition processes such that the source material particles face less obstruction due to the air and other gas particles inside the deposition chamber and can move over a large distance. There are a large number of national and international units for the measurement of vacuum. The most commonly used units are Pascal, bar and torr. By dropping the air or gas pressure inside a closed chamber where reducing the quantity of gas particles, vacuum can be generated. There are basically two ways of doing it. First, by displacing the gas molecules from the closed chamber either into the atmosphere or into an external place. Gas particles may be condensed, absorbed or chemically combined within the vacuum system. An extensive range of vacuum generators is known these days in which all of them work accordingly based on the different technical principles and methods. These vacuum generators are categorized under the term vacuum pumps. According to their mode of operation, vacuum pumps are classified into three distinct types. The first type is positive displacement pumps, capturing, condensing and expelling the gas particles outside the chamber. The example of the positive displacement pumps are mechanical pumps. The second category is the momentum transfer pumps, in which gas particles gain a preferential direction. And the example of momentum transfer pumps are diffusion pump and turbomolecular or TMP pump. The third category is adsorption or reaction pump, in which the capturing and keeping the gas particles is involved. The example of adsorption or reaction pumps are cryopumps, sorption pumps, and ion pumps. According to the grouping of pressure ranges, vacuum systems are classified into 5 categories. The first category is the rough or low vacuum, in which the pressure is greater than or equal to atmosphere to 1 torr. Second range is the medium vacuum, in which the range is from 1 torr to 10 to the power minus 3 torr. Third one is high vacuum, in which the range is 10 to the power minus 3 torr to 10 to the power minus 7 torr. Then next comes the ultra high vacuum, in which the range varies from 10 to the power minus 7 torr to 10 to the power minus 11 torr. And finally and lastly, there is extreme high vacuum, in which the range is greater than 10 raised to the power minus 11 torr. The different type of pumps for these ranges of vacuum can then be divided into the following category. First one is the primary or backing pumps, by which we can get the rough and low vacuum pressure ranges. Second one is the booster pumps, in which we can get rough and low vacuum pressure ranges. Then there comes the secondary or high vacuum pumps, in which high, very high and ultra high vacuum pressure ranges can be obtained. The fundamental principle of operation of working of all the vacuum pumps is same apart from their design. The function of the pump is to remove the molecules of air and other gases from the vacuum chamber or from the outlet side of the higher vacuum pump if connected in series. At the same time, as the pressure in the vacuum chamber is reduced, the task of removing additional molecules becomes exponentially harder. As a consequence, a developed vacuum system containing deposition chamber and vacuum pumps must be able to operate over a portion of an extraordinarily large pressure range, which typically varies from 1 to 10 raised to the power minus 7 torr of pressure. You can see in the given figure, figure 1, the vacuum system containing deposition chamber and vacuum pumps. In the upcoming sections, we will discuss the fundamental principle and working of the diffusion pump, which is a secondary high vacuum pump which has a range from 10 raised to the power minus 3 torr to 10 raised to the power minus 7 torr. And it works on the principle of momentum transfer. The principal operation of diffusion pump. Diffusion pump is classified as a momentum transfer pump, also known as molecular pump. The fundamental principle of working lie on the use of high-speed jets of dense fluid, which helps to move the gas molecules out of the deposition chamber. Positive displacement pumps, commonly called as mechanical pumps, are used in conjunction with the momentum transfer pumps to achieve high vacuum. Momentum transfer pumps in conjunction with displacement pumps comes under the category of gas transfer pumps, operated by transferring the gas molecules by either momentum exchange, which is a kinetic action, or positive displacement. When the gas is expelled from the pump, it is slightly above the atmospheric pressure as the same number of gas molecules is discharged from the pump as they enter it. Compression ratio of the gas particles is defined as the ratio of the exhaust pressure to the lowest pressure obtained. That becomes the ratio of the outlet to the inlet, because exhaust pressure is the outlet and the lowest pressure obtained is the inlet. Mechanical pumps, commonly referred as positive displacement transfer pumps, are based on the mechanically trapping of a volume of gas particles and moving them from beginning to end of the interior of the pump. Mechanical pumps are commonly designed in compound stages on a common drive shaft in order to expel the gas particles outside into the atmosphere. The total gas volume is compressed to a smaller volume at a higher pressure, or to the next pump, as we can see in figure 2. Thus, the diffusion pump and mechanical pump are used in series to provide a high vacuum with high flow rate. In the figure 2 given below, you can see the positive displacement pump having an inlet port and the outlet port. Then there is a vane rotor and casing. Using high-speed blades or by introducing vapors, the kinetic transfer pumps, which works on the principle of momentum transfer, directs the gas particles towards the pump outlet and thus provide the increased probability of gas particles moving towards the outlet of the pump. Kinetic pumps can achieve high compression ratios at low pressures in spite of the fact that they do not have any sealed volumes. So now let's discuss about the working principle of the diffusion pump. Diffusion pumps fundamentally work on the principle of momentum transfer by creating the jet of oil vapors. In the interior of the pump, the high-speed vapor molecule of the created jet collides with a gas particle and transfer their momentum to the gas particle, thus directed it towards the preferred direction through the pump. The detailed assembly of the diffusion pump is shown in figure 3. So figure 3 given here shows the basic pump design, in which you can see there is an inlet, then there is a cylindrical water cooled body, there is an exhaust and oil reservoir, heater is there to provide the heat, there is an ejector, then there is a thermal protect switch, and there is a multi-stage jet assembly. The bottom of the diffusion pump contains an oil reservoir below which an electric heater is placed to boil the oil. The oil is boiled to a significant limit so that it vaporizes. The vapors of the oil rises up through the center assembly of the pump towards the upper direction and exits from the nozzles via jet assembly in a downward approach. The process of vaporizing the oil and formation of jet must be performed at a reduced pressure. This implies that for the operation of a diffusion pump to get started, a significant value of vacuum must be present, or the assembly must be roughly pumped down to an acceptable pressure, typically 100 millitorr. In the absence of the force vacuum, no pumping action by the diffusion pump is performed and the pumping fluid will get damaged. The multi-stage assembly of the jet is present in the form of ring and form a jet of vapor that extends from central part of the pump, exit from the nozzles and end up after colliding with the pump wall. The gaseous particles that are roaming into the inlet collides with these vapors particles are confined. After colliding with the water-cooled walls of the pump, the oil vapors cools down and settles back at the bottom of the pump, running through the walls of the pump and finally reaches the reservoir. Through this phenomena, the oil vapor jet completes its one cycle and releases off its confined gas particles, thus ready to begin for the next cycle. Therefore, the gas particles which are approaching towards the upper direction is confined by the oil vapor jet and exhausted towards the downward direction again. After certain number of cycles, in an area of higher pressure is created at the bottom of the pump than at the top of the pump. Therefore, during the operation of the diffusion pump, higher pressure is created below the oil vapor jet as compared to above that jet. At the bottom of the pump, the pressure is high enough for the gas to be pumped out by a standard mechanical pump. In the complete process, the oil vapor jet is always preferred to move in the downward direction, but it is quite possible for some of it to approach towards the upper direction at the top of the pump. In order to avoid this situation of migration of oil vapors into the chamber, a cold trap is situated at the top of the jet assembly so that the vapors can be condensed in that area. The chamber is evacuated through the pump via concentric circular baffle which is placed in between the cold trap and the pump. Baffle allows gas particles to wander in but traps the oil vapors. Commonly, silicon oil is used as the diffusion pump oil due to its high stability and high vapor point. The performance of the silicon oil is reported well over a long period of time with very low degradation. Silicon oil is also relatively much safe than any other in case of toxicity and flammability. The foremost criteria of using silicon oil is that the operation of vaporizing it is performed in low pressure and it must not be exposed to air when heated, otherwise the oil will get spoiled. Now let us discuss the parameters influencing the functioning of diffusion pump. The first parameter is the compression ratio. Compression ratio of the diffusion pump is the ratio of the exhaust pressure to the inlet pressure. For most of the gases, the compression ratio is very high. For example, the compression ratio created is 1 million for an inlet pressure of 2 into 10 raised to the power minus 7 torr and a 4-line pressure of 2 into 10 raised to the power minus 1 torr. Since the compression ratio is different for gases having different molecular weights, thus, in a mixture of gases, each gas may be pumped with different effects and can have different flow rates. For example, the compression ratio for hydrogen will differ greatly from the compression ratio for argon. The second parameter influencing the functioning of diffusion pump is critical discharge pressure. The critical discharge pressure of a diffusion pump is the maximum allowed pressure at the 4-line during normal pumping operation. The diffusion pump doesn't perform efficiently if a critical discharge pressure is not appropriate. As a consequence, the discharged gas particles do not have sufficient energy and density to provide a barrier for the air in the foreline, and the particles will carry the oil vapors in the wrong direction. The maximum allowable foreline pressure for the normal functioning of the diffusion pump is about 0.5 torr. Thus, the most important rule for the functioning of the diffusion pump is to maintain a significant amount of critical discharge pressure. The next parameter is the back streaming. The pumping fluid can pass through the inlet port of the pump and also in the opposite direction to the favored direction of gas flow. This process of undesirable flow of pumping fluid is called backstreaming. The process of backstreaming also must include the trap, baffle and plumbing as well as in addition with the pump, because all these parameters has a great influence on the rate of transfer of pumping fluid vapors from the pump assembly to the deposition chamber. Following are the conditions that can cause backstreaming. The first condition is the foreline pressure exceeds the critical discharge pressure. Secondly, exceeding maximum throughput capacity for long periods of time. And thirdly, wrong procedure of startup or shutdown also causes backstreaming. In case of thin film deposition, the process of backstreaming is a terrible phenomenon. When backstreaming oil comes in contact with the hot filaments or electrical discharges, it results in carbonaceous or siliceous deposits. Diffusion pumps are not considered as a suitable pump for use with highly sensitive analytical equipment or any other applications which require an extremely clean environment due to the process of backstreaming. Baffles and liquid nitrogen cold traps are used to minimize the backstreaming. The fourth parameter is baffles. Baffles are placed in between the cold trap and the pump to reduce the backstreaming of oil vapors into the deposition chamber. Baffles do obstruct the flow of pumped gases, but well-designed units can retain about 60% of the pumping speed. Baffles are placed in conjunction with the water-cooled traps, which can reduce the rate of re-evaporation of condensed oil vapors and thus reducing the density of vapor in the between of baffle and the trap. The next parameter is traps. The cooled traps are placed above the baffle and can serve two purposes. Firstly, act as a wall in the path of the oil vapors from the diffusion pump to deposition chamber. Secondly, they also provide as cryopumps for condensable vapors derived from the system. The pumping speed for water vapors can be increased by using liquid nitrogen traps and thus lower the base pressure. The last parameter and the sixth parameter is the fluids. In the early development of the fluids, most of them can create the vapor pressure of about 10 raised to the power minus 7 torr. Thus, the chamber pressure of the system was limited to this range. The market then revised up to great extent after Hickman proposed the use of polyphenol ethers as a fluid. which shows exceptionally high thermal and chemical stability. Later on, the characteristic of the silicon fluid DC705 was also found to be admirable as another low vapor pressure fluid. The operational feature of these fluids will allow the base pressures to reach 10 raised to the power minus 9 torr limit. Recently, fluorinated oils have been also developed as a fluid to use in diffusion pumps, as they have the advantage of compatibility with corrosive gases used in some deposition processes. So let us now discuss about the advantages and disadvantages of diffusion pump. The advantages of DP or diffusion pump are simple geometry of assembly. Secondly, it has comparatively lower cost than other high vacuum pumps. Thirdly, pumping rate is linear. The fourth one is diffusion pumps are much easier to operate. Fifth one, the diffusion pumps do not cause any vibration or noise. And lastly, there is low maintenance as in terms of the diffusion pump. Now let us discuss the disadvantages of diffusion pump. Number 1, diffusion pump require oil as a fluid to pump. Secondly, it requires significant value of 4 vacuum to operate. Thirdly, in case of backstreaming, the deposition chamber can be contaminated. Number 4, diffusion pump require cold trap. Number 5, diffusion pump require ample of time to vaporize the oil. Now in the end, let us discuss the startup of diffusion pump. There are certain set of steps. The first step is all the valves should be closed. Secondly, start the mechanical pump or the rotary pump. Then next, open the 4-line valve. Rough pump the diffusion pump to about 20 millitorr. Fourthly, fill the liquid nitrogen in the cold trap placed above the baffle. Then next, turn on the heater of the diffusion pump to boil the oil so that it can vaporize. Then next, close the 4-line valve. Now, open the rough valve of the deposition chamber. Evacuate it up to 100 millitorr. Now, close the rough valve and open the 4-line valve. Then next, open the baffle after checking the level of liquid nitrogen in cold trap. And lastly, switch on the high vacuum gauge or the ionization gauge. Now let's discuss about the shutdown of diffusion pump. First of all, close the baffle first and then turn off the ionization gauge. Secondly, turn off the heater and allow 30 minutes to cool the oil. Next, warm the cold trap to room temperature. Then close the 4-line valve. And lastly, vent the diffusion pump via vent valve. So students, let us summarize what we have learned in this module. First of all, we had a brief introduction on the diffusion pump and we learned about the principle on which the diffusion pump works. Secondly, we learned about the working principle of diffusion pump in detail along with the schematic diagram, and we learned about the various parts of the diffusion pump. Thirdly, we studied about the parameters influencing the functioning of diffusion pump and which parameters can cause the obstruction and which parameters are most crucial while the working of the diffusion pump. Next, we studied about the advantages and disadvantages of diffusion pump, and in the end, we learned the method or we learned the steps for the startup and shutdown of the diffusion pump. Thank you.